Hello everyone, how are you all? I hope you all are fine and safe. Welcome back to Quantum Mathematics. I am Aman. Today again I'm back with a very interesting video, and I hope you can see this right over here, and maybe you just have seen the thumbnail by which you came here. In this video, I'm just going to talk about gamma function in detail, right? Just we are going to deal with some like the introduction and factorials, and I've written here over here. Yeah. We are going to derive gamma of 1 over 2 with two ways, and we are going to generalize a very fascinating integral. You will get to know that, and let's just begin our video because we are going to deal with gamma function, and we just have we're gonna take a lot of time maybe, but yeah, I'll do it. And I think I'll continue this series later on, by which I will have a new video after this video on beta function, right? Because I'm just going to done, or maybe if you request me to just bring some questions of gamma function, I'll do it for you, don't worry. And but I'm thinking to just bring a new video on gamma function, and if you would like to have some questions on beta function, you can just comment me. I will just provide you a PDF in which you can have a lot of questions of gamma function, right? Okay, so now let's begin our journey. And yeah, so what is gamma function? Okay, it's my perspective, right? It's a representation of factorials. So basically, firstly, let's talk about an integral, let's say I, right? So we're just going to talk about this. The integral from 0 to infinity of x to the n minus 1 t to the negative x dx. Okay, so if you have seen gamma function like if you have seen gamma function earlier in your life, so you might have been like, what do you call it? Encountered with this representation. Actually, this is going to be the gamma function evaluated at n, but I'm not going to write it down for now, and I will prove it for you, right? It's a representation of factorials, that's it. So this is our introduction, and we are just going to we're just going to integrate this, we're just going to solve this, and we're going to have a very good result. So let's solve this. So basically, I'm having two functions. Firstly this function and then this function, right? So if I'm having two functions in as an integrand, then I'm just going to use by parts, and my favorite method is DI method, as you all know if you have been continued on my YouTube channel. So yeah, this is how it works. So I'm just going to differentiate x to the n. Actually, I need more space. So yeah. So okay. So I'm just going to differentiate. You can choose up. It's up to you, like which function you should differentiate or which function you should integrate, because both the functions are differentiable and integrable at the same time. But for the sake of like evaluation of gamma function, I am just going to take this function as my differentiated, and this function as integrand. Okay, so x to the n minus 1 and e to the minus x, right? When you differentiate this, it's n minus 1 times x to the n minus 2, and when you integrate this, it's e to the minus x. Again, when you differentiate this, n minus 1 times n minus 2 times x to the n minus 3, and again when you integrate this, it becomes e to the negative x again, because when you integrate this, it becomes negative. So when you again integrate this function, so you're gonna have a negative. So basically, negative times negative is just positive, right? Okay, and again when you differentiate this, so this becomes n minus 1 times n minus 2 times n minus 3 times x to the n minus 4, and I don't need to write. This goes up to plus. Actually, the last term would be plus, and I will show you why. But for now, let me just write it down. Okay, so you would ask me, Aman, how did you just guess that this term is positive, it could be negative, right? But if you just have a look at this pattern, so you might know that how this works is something like that, right? Actually, and yeah, so this times this, I'm talking about the integrand that we are going to left with after all the terms. Okay, I'll tell you, just be patient, right? So this becomes n minus 1, n minus 2, n minus 3 dot 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 3 times 2 times 1. Okay, so, and this is inside an integral. I hope you all know about that. So let me just write it down on this board. So our I is, okay, this times this, it means minus of x to the n minus 1 e to the minus x, and then this times this, so minus of n minus 1 x to the n minus 2 e to the minus x, then again minus n minus 1 n minus 2 x to the n minus 3 e to the minus x, and this goes evaluated from 0 to infinity, right? Okay, and now we are just going to left with the last term, that is plus, because eventually if like I'm having these two things as positive, if I'm multiplying, right? If I'm multiplying these two things at each term, these two things, I'm just going to have positive. That's why I guessed it. Last term would also be positive instead of negative. I hope you understand that. That's why. So this is a constant. So this becomes n minus 1, n minus 2, n minus 3 dot 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 3 times 2 times 1, and times the integral from 0 to infinity of e to the negative x dx. Actually it's negative, I just missed the negative sign, right? Okay, so if you look closely inside this big bracket, so when you plug x equals 0, so this becomes 0 times anything is 0, 0 times anything is 0, 0 times anything is 0, right? So everything is going to be 0. And what about the upper limit? That is infinity. So please note it down that e to the negative infinity is always 0. So when you plug infinity inside this parenthesis, so this becomes e to the negative infinity. I hope you can see here, e to the negative infinity times anything is 0, e to the negative infinity times anything is 0, everything is gonna be 0, right? So basically this is gonna be 0. So we're just going to left with our I is, I hope you know what this is all about. It is n minus 1 factorial. This is a representation, right? So now talking about the integral dx. So let's talk about this integral right over here. So when you integrate this, it becomes negative e to the negative x evaluated from 0 to infinity. So negative of e to the negative infinity minus e to the minus 0, right? So this becomes minus of 0 minus 1, that is 1. So again, this whole integral is being collapsed with 1 only, and we are finally left with as I is n minus 1 factorial, and this is what gamma of n is all about. So this is what a basic or a representation of gamma function. So please remember that gamma of n is n minus 1 factorial, right? This is all about, and now we are good to go with some properties of gamma function, as well as we are going to generalize some integrals, as well as we are just going to tackle what is gamma of half in two different ways. I'm very excited about that, because I'm just going to use the gamma function itself to derive it, and then after I'm just going to use a very classic, a realistic and amazing result, the Euler's reflection formula that says, let me just write it down over here, and if you want I can prove it down over here, but not right now. But yeah, if you want, just comment it down. I'll bring a new video for that also. So this is what Fourier's reflection formula is all about, right? And maybe I have proved it down in a video. Yeah, I did. Actually, I did prove that this equals the square root of pi in a video, but yeah, again I'll do it for you guys right now. This is very amazing, and please noted, please be careful that yeah, it's all right. Okay, I'm not going. I'm not going